Hello students, Jai Swaminarayan. I am Professor Urvish Mewada, HOD Electrical Department, Sri Swaminarayan Institute of Technology, Bhat Gandhinagar. I am the subject matter of Interconnected Power System subject, which is in the 7th semester Electrical Engineering, and the GTU subject code of this subject is 2170901. Students, we are currently discussing the chapter number 3, Load Flow Studies. In chapter number 3, today we are going to discuss the topic number 5. In last lecture we have discussed about the Gauss iterative method and the Gauss Seidel method in detail, means all the algorithm and flowchart and the examples related to the Gauss Seidel method. Now today we are going to study the third method for the load flow study is the Newton-Raphson method. Now let us discuss the Newton-Raphson method. So basically it is the introduction of the Newton-Raphson method. So the NR method we can indicate it with the NR method also. So the NR method is important method which is solving for the non-linear algebraic equations. So means we can apply this for the power system where the load is varying, or we can say the system is continuously fluctuating, where we applied the Newton-Raphson method for the solution. Now it only having a drawback is that it has the drawback is the large computer memory is required, because it performs the large iterations, and for that the large computer memory is required, so that it is only a drawback of NR method. Now let us discuss the NR method. So let us start with the NR method for single valued function. So this is the basic solution of the NR method. So let us consider that a single value equation where the f is the function of x is equal to 0. Now the solution of this equation is the value of x at which the fx is equal to 0. So let us start with a guess for the x as x raised to 0, means we start all the iterations, or we can say the solution we start with the x raised to 0, means this is the first iteration. Now we assume the first iteration value x comma x raised to 1 as the solution, where means it will get increase if we not get the sufficient output or the desired output. Then we can extend the number of iteration until we get the desired output. So x raised to 1 is equal to x raised to 0 plus delta x raised to 0. So this is the formula to find out the iteration of the x raised to 1. Now f is the function of x raised to 1 is equal to f is means f function is taken out as a common, so x raised to 0 plus delta x raised to 0 is equal to 0. So this is the condition needs to be satisfied. In above equation, delta x is equal to 0 is not known, so that's why if we put the number of values of the say previous data, then we can get the output of the next consequent iterations. But it can be estimated by like expanding the above equation as the Taylor series that we already studied in the our higher engineering mathematics. So the result is found to be like the series listed below. So f is a function of x raised to 0. So this is the equation for which we are writing the Taylor series. So f is the function of x raised to 0 plus del f by del x raised to 0 into delta x raised to 0 plus 1 upon 2 factorial del square f by del x square raised to 0 into delta x raised to 0 square. So this is the series for we can use to find out the solution of the single valued function. So the symbol del f by del x raised to 0 stands for the value of say del f function of x. Del x is equal to say at x is equal to x raised to 0. So by putting x is equal to x raised to 0, we can find the solution of the respective iterations. Now first that estimate of the correction is made by the say connecting the series after the first two terms, then the function f x raised to 0 plus del f by del x raised to 0 into delta x raised to 0. This is the first function that we are taking to determine the solution. Now from the above equation, the value of delta x raised to 0 is can be determined with the help of this. So make this del f by del x raised to 0 as a function, then that will be f x raised to 0 divided by the del f by del x. So this will be the equation to find out the delta x raised to 0. By putting this value in our delta x raised to 0, we can find out the value of x raised to 1. The first iteration value of the x raised to 1 now can be calculated, that we had this equation in the previous slide, that is x raised to 1 is equal to x raised to 0 plus delta x raised to 0. So the r plus 1th iteration, r is the number of iteration, so the iteration we can determine from this r plus 1th iteration value, that is x raised to, this is the 1, so this is the first iteration. Now x plus 1 is equal to x plus delta x, where the first we are estimating the root is that x raised to 1 is equal to x raised to 0 plus delta x raised to 0, that is taken out from this. So x raised to 0 plus this is the value for f x raised to 0 del df by dx. We can take the first estimate of the root. So this is the equation that we are going to use to determine the value of the first iteration. Now the r plus 1 is the estimation of the root, so x is x raised to r plus 1, so x raised to 0 will become x raised to r plus delta x raised to r is equal to x raised to 0 again will become x raised to r, because r stands for the number of iteration, minus function x raised to r and df by dx raised to r. So the iterations are continued till this condition will get satisfied, that x raised to r plus 1 minus x raised to r less than or equal to epsilon, where epsilon is the specific tolerance limit of the solution that we need to determine. Now let us solve one example related to this, so that will be more clear. So example indicates that the find the value of x, that indicates the find the value of x in the equation f is the function of x square minus 3x plus 2 by using the Newton-Raphson method. So let us consider how to solve this equation using the NR method. So the given equation is, say, fx is equal to f of x is equal to x square minus 3x plus 2. So over here the differentiate f of x with respect to x. So over here d by dx fx is equal to this will become 2x, and 3x will become minus 3. So this is the value after the differentiation. Now let the initial approximation, that will be x raised to 0 is equal to 0. So f of x raised to 0 is equal to 0 square minus 3 0 plus 2 is equal to 2. So function of x raised to 0 is equal to 2. Now df of x divided by dx raised to 0 is equal to 2 into 0, because this x is 0, so 2 into 0 minus 3 is equal to minus 3. So this is the value that we determine with the help of the differentiation of the equation. Now the first estimation, that we take the equation from the previous theory, means the theory that we explained, x raised to 1 is equal to x raised to 0 plus delta x raised to 0. So x raised to 0 plus minus function f of x raised to 0 df by dx raised to 0. Now the value that we determine minus f of x raised to 0 is minus 2, and df by dx raised to 0 is minus 3. So this is the value of x raised to 1. This is the value of x raised to 1. Now similarly consecutive iterations value can be determined from the previous equation. Now this x2 is equal to for that we take the value of the previous equation. Now that is 0.6667. so this is the value of x1. So equation is x1 x raised to 1 minus x raised to 1 square minus 3 into x raised to 1 plus 2 divided by 2 into x raised to 1 minus 3. So this is the equation that we are going to use, and by putting this values we can get the values of x2. So this is the value that we determined from from the x1, so 0.6667 minus 0.6667 square minus 3, and by putting all the values we can get the value of x2. Now we use the value of x2 to determine the third iteration of x raised to 3. So by putting instead x raised to 1 we put the x raised to 2 over here, and by putting all the values of x2 over here we can get the values of x raised to 3, that is the third iteration value. Now after the third iteration we use this value of third iteration for the solution of the fourth iteration, and we follow the same equation that we followed in the x raised to 2, x raised to 3. So by putting the value of x raised to 3 in the fourth iteration we can get the value of 0.999. So this is the value of the fourth iteration. Now the fifth iteration that we are going to determine is with the help of the fourth iteration we put the value of the answer of the fourth iteration in this equation, and after putting the values of x raised to 4 in this equation we can get the value of x raised to 5, and this is the value that we get after x raised to 5. And when x is equal to 1 the function of 1 is equal to 0. So that's why this condition is satisfied, and hence the root of the equation is x is equal to 1. So by putting function of x raised to 0, so function of x means f of 1 is equal to 0. So this is the condition which gets satisfied after the fifth iteration. So we can stop the number of the performance of the iteration, and this will be the solution after the by putting the values of the previous consecutive iterations into the next consecutive iterations, and this will be the answer of the single valued function. So this is how we can calculate the examples related to the single valued functions. Now let us discuss the NR method for the multi-valued function. So now let us discuss the NR method for the multi-valued function. So let us apply NR method for the system of equation where the number of unknown is more than 1. So in the previous case we had only one unknown, in this we have the means more than one unknowns. So as an example we consider the two algebraic equation with unknown functions, say x1 and x2. So function of 1 is equal to x1 and x2 is equal to 0, and function 2 f2 is equal to x1 x2 is equal to 0. So these two are the equation. Let x1 raised to 0 and x2 raised to 0 be the initial estimates of the unknown x1 and x2, and delta x1 raised to 0 and delta x2 raised to 0 are the correction which when added to the x1 raised to 0 and x2 raised to 0 give the correct solution of the given multi-valued function using NR method. Then function f1 will become x1 raised to 0 plus delta x1 raised to 0 comma x2 raised to 0 plus delta x2 raised to 0 is equal to 1. Similarly we can write the f2 function f2 x1 raised to 0 plus delta x1 raised to 0 comma x2 raised to 0 plus delta x2 raised to 0 is equal to 1. Now expanding equation 3.31 in the Taylor series, so here we are again applying the Taylor series. So f1 x1 raised to 0 comma x2 raised to 0 plus df1 means del f1 by del x1 raised to 0 into delta x1 raised to 0. This is the first value of the Taylor series. Now this is the df1 by dx1 raised to 0 into delta x2 raised to 0. So we are using both the function in f1. Now f2 this will be the same equation, but here the function is 2, that's why the del f1 will become del f2 over here. Only this is only a change of the previous functional equation. Now where del f1 by del x1 raised to 0 denotes the partial derivatives like del f1, and the functions are x1 and x2, and the del x1 is the with respect to this x1 we are deriving evaluating the equation. So evaluated as x1 is equal to x1 raised to 0. So while keeping x2 as constant, similarly the other terms in equation 3.32 can be evaluated, means means when we consider that the x2 function is constant, then we can have the value of the means we can have the solution of the either values, and the matrix form of the equation 3.32 appears as like this. So df1 by dx1 and df1 by dx2, del f1 by del x1, del f1 by del x2, and del f2 by del x1 and del f2 by del x2. So these are the function, means the multiplication del x1 raised to 0 and del x2 raised to 0 is equal to minus this is the positive term, so we are taking it over here, means at the right side, and this will become the equation for this function. So this will this quantity will become minus. So f1 x1 raised to 0 x2 raised to 0 minus f2 x1 raised to 0 x2 raised to 0. So the condensed form of this above equation can be write that j is j raised to 0 delta x raised to 0 minus f raised to 0. So from that we can write this means again an equation like this to be the similar equation, or we can say f raised to 0 is equal plus j raised to 0 delta x raised to 0 is equal to 0. So this is the equation which is the condensed form of the equation 3.32. Now let us discuss the first estimate of the correction is, say delta x raised to 0 will be j raised to 0 raised to minus 1 and means the function 0. So the first estimate of the root is x1 is equal to x1 x raised to 0 plus delta x raised to 0, and the rth plus 1 is the estimation of the root. That's why this is the number of it, the r indicates the number of iteration. So this will become x raised to r plus 1, and x raised to 0 will become x raised to r, and delta x raised to 0 will become delta x raised to r, where r is the number of the iteration. Now as before, the estimation are continued till this is the condition that must be that needs to be satisfied. So that is x raised to r plus 1 minus x raised to r less than epsilon, where epsilon is the tolerance of the the iteration that we found using an r method. Now equation 3.34 that again can be generalized for the nth unknown variables for the n that's simultaneous algebraic equations are, say delta f1 raised to 0 to the function delta f n raised to 0, means nth number of the function. For the nth number of function we can find the solution using the multi-valued function theory using an r method. So this equation will become df1 dx1. This is the matrix that we form in the previous slide. We are just writing the nth number of the we are considering the nth unknown and nth simultaneous algebraic equation. That's why we are putting instead of 1 we are putting n. So this f1 will become fn, and we are finding the function x1. That's why del x1 will remain same remains as it is. So df1 d x1 will become xn over here, and over here dfn is the del f. This f1 will become del fn del xn raised to 0, and x1 delta x1 raised to 0 delta xn raised to 0. So this will be a function, say 0 is equal to 0. So we form this for this equation. Okay, now let us discuss the example related to this, then so that this will be more clear to get the solution of the multi-valued function using an r method. Now the function x1 x2 is equal to, this is the equation x1 square plus x2 square minus 4, and the function g, or over here this is the function number 2, f is x1 x2 x1 square plus x2 square minus 1. So assume x1 raised to 0 is equal to 2 and x2 raised to 0 is equal to minus 1. These are the assumptions that we are that is given into the data, and update the value of x1 and x2, perform one iteration. So we are going to put the we are going to find out the updation of the values of x1 and x2, and we need to find out the consequent iteration of the given data. Now the solution. So the solution gives that the function x1 x2. So the equation df del f by del f1 is the 2x1, because we are finding this in terms of x1, so 2x1, and del f by del x2, this is the x1, this is the printing mistake, del x2 is equal to minus 2x2. Now del g by del x1, so that is 2x1, and del g by del x2 is equal to 2x2. So these are the values that we find out after the derivation of the given equation. Now the Jacobian matrix that we can form with the help of the equation J is equal to del f1 by del x1, so del g by del x1, and del f by del x2, del g by del x2. This is the function of say x1 and x2. So the values that we determine with the help of the derivation in the previous case, we are putting this value. So del f by del x1 is the 2x1, del f by del x2 is minus 2x2, and del g by del x1 is 2x1, and del g by del x2 by 2x2. So assume that x1 raised to 0 is equal to 2 and x2 raised to 0 is equal to minus 1, that is given into the data. So j raised to 0 will become 2x1 raised to 0, 2x2 raised to 0, 2x1 raised to 0, and 2x2 raised to 0. So x1 raised to 0 is the 2, so this will become 4, and x2 raised to 0 is minus 1, so minus 2 into minus 1, that will become plus 2, and 2x1 raised to 0 is the say 2, so it is 4, and 2x2 raised to 0, this will become minus 1. The coefficient matrix elements are, say, the function f of x1 and x2 is x2 square minus x1 square minus x2 square minus 4. So put x1 raised to 0 is equal to 2, and x2 raised to 0 is equal to minus 1 in this function. So function x1 raised to 0, x2 raised to 0 is equal to this is the x1, so raised to 0 is 2, so over here 2 square minus of x2 raised to 0 is minus 1 square minus 4. This will be the function of x1 raised to 0 and x2 raised to 0 is equal to minus 1. Then put x1 raised to 0 is equal to 2 and x2 raised to 0 is equal to minus 1 in function x1 raised to 0 and x2 raised to 0. So 2 raised to 2 square minus 1 square minus 4 is equal to minus 1. So similarly, g x1 raised to 0, x2 raised to 0 will become 4 by putting the values of x1 raised to 0 and x2 raised to 0 from this equation. So the coefficient matrix, say f function raised to 0 is equal to minus 1 and 4. So this is the value that we get after putting the values of the functions in the Jacobian matrix equation. So now the inverse Jacobian matrix will become 0.125 after solving this. So inverse means 1 upon minus 1 by 4, so this will become 0.125 and 0.125 and 0.25 minus 0.25. So this is the inverse matrix of say the Jacobian matrix that is given, that we solve over here. Now so the increment matrix can be obtained as follows, that delta x1 and delta x2 raised to 0 is equal to minus j raised to 0 raised to minus 1 and function f raised to 0. So these two are the values that we have in the matrix form. So that is 0.125, 0.125, 0.25 and minus 0.25, and this is the minus value. So that's why the minus is indicated over here. Now function of function means raised to 0 matrix is minus 1 and 4. So by after solving this two matrix, the value of delta x1 and delta x2 raised to 0 is minus 0.375 is the delta x1, and delta x2 is the 1.250. So the updated values of the x1 and x2 are x1 raised to 1 is equal to 2 minus, this is the value that we determine from this. So that is delta x1 is 0.375, so that is 1.625, and the x2 raised to 1 is minus 1 plus 1.250. So x2 raised to 1 is 0.250. So this is the value of the consequent iteration that we can find with the help of NR method, multi-valued NR method. So this is the solution for the multi-valued NR method, multi-valued function of the NR method. Now till that we use NR method for the single valued function and the multi-valued function. Now now we are going to use the NR method for the power flow solution. Now to apply the NR method for the solution of the power flow equation, generally we solve bus voltage and line admittance in polar form. So that's why we are taking the from the equation 3.8 and 3.9, that is that we already discussed in the bus classification, that is pi is equal to f1 del and mode v, and qi is the f2 del mode v. So from this we can write the equation of pi and qi that we already derived, that is sigma k is equal to 1 raised to n. Vi is the voltage of the nth number of bus, means the bus itself. Vk is uh, uh, the voltage of the load bus, and this is the yik admittance of the all the links, that links and all the buses, and cos theta ik plus theta k minus theta ik plus delta k minus delta I. So delta is the phase angle, or we can say power angle of the circuit. Now this equation will become pi mode v delta. Now qi will be minus sigma k is equal to 1 raised to n vi vk yik sine this is the reactive power, that's why this is the sinusoidal quantity theta ik plus delta k minus delta I. So over here the equation will become qi mode v delta. So this is the equation of the active power and the reactive power of the power system. Now the real and reactive power are the function of, say, mode v comma delta. So that's why mode v is equal to v1 v2 to vn raised to nth number of voltages of the respective buses, and delta is the delta 1 delta 2 delta n raised to t. So this is the phase angle of the respective buses. Now pi is the function of, say, v mode v delta is equal to pi into x, and qi is the mode v delta, so qi into x. Now in this, the x is equal to the delta by mode v. So this is the equation to determine the x. Now in terms of iterative, x should tends to the value which makes the pi minus pix is equal to 0. So that's why qi minus qix is equal to 0, where pi is equal to p scheduled, means the power that which is scheduled for the power system. So that's why pi into x is equal to px. So from that we can have the calculated value at the load bus. Similarly we can write this equation, means this is the assumptions, or we can say the data from the for the reactive power. So that is qi is equal to q scheduled and qix is equal to px. So this is the calculated value at the load bus. So these are the values that we can determine using the NR method. So let us put this into the matrix form. So we get in matrix form function of x is equal to p schedule minus px and q schedule minus qx. So this will be the delta px, means change in the power, because this is the value from which we can say that this is the change in the power respective to the number of buses, and this is the change in the reactive power with respect to the number of buses. So x stands for the function for which we are performing the iteration, so this will become 0. Now delta pi is equal to, we are writing the series for delta pi is equal to del pi by del p2 del theta 2. So this is the series that we can write for the consequent say power angles. Say del pi by del theta 2 is the delta multiplied by delta theta 2 plus del pi by del theta 3 into delta 3 theta 3 plus del pi del delta 4 into delta delta 4. So from that the fx is equal to delta px and delta qx is the Jacobian matrix that we can write for the two buses system. Say minus j11 is the function of x, minus j12 is the function of x, j21 minus j21 is the function of x, and j22 is the x, the value that is that we determine x is equal to v by delta theta. So from that we can write this delta theta into delta mode V. So this is the fx equation. Then Jx is the Jacobian matrix. So for J11x is the value that is del pi x into del delta k. So for that J12 and J21 and J22 we can write the equation from this given matrix multiplication. Now where I is equal to 2 to n means this is the number of buses, and k is the link that we are going to use for the interconnected power system. So k is the 2 to n. So from the equation 3.39 and 3.40 that we already write, we can write the equation del pi into x into del delta k is equal to sigma k is equal to 1 and k is not equal to I, because we have taken this iteration for the from the we are starting from the bus number 2, because we have taken bus number 1 as a slack bus for the solution raised to n. So vi into vk yik sin theta I minus plus delta k minus delta I, where I is equal to k, and del pix by del into vk, that this will become vi mod vi mod yik cos theta ik plus theta k delta k minus delta I, where I is not equal to k. So after solving this we can have the value that is 2 into vi into vii cos theta ii, plus this is the value that we are going to put sigma k is equal to 1, k is not equal to I raised to n, then mod vk yik cos theta ik plus theta k minus theta I from this equation. Now from the equation 3.9 and 3.30, so this is the equation that we already discussed from the in the previous slide. This is the equation that we discussed. Now for I is equal to k del qi x by del k del delta k. So for that we are writing this equation by putting these values. This is the solution. Say vi mod vi into mod yik into mod vk and cos theta ik plus theta k delta k minus delta I, where I is not equal to k. So for this we have the solution that is sigma k is equal to 1, k is not equal to 1 raised to n. This is the value that we put the for the nth number of iteration where I is equal to k. So for that the del qi x into del vk will be, this is the equation. For that the solution that is 2 vi yii sin theta ii plus sigma k is equal to 1, k is not equal to I. This is the value that we are going that we placed from the previous equation. So from that we can say that for I is equal to k, the Jacobian matrix, say h n j and l are the we can say we use the operators. So hik is equal to del pi into del theta k, and nik is equal to del pi by del into mod vk, and where gik is the del qi by del delta k, and lik is equal to del qi into del mod vk. So this is the Jacobian matrix which is arranged for the for to obtain the approximate correction, where I is equal to 2 to n and k is equal to 2 to n. So it indicates the number of buses and the number of nth number of branches. So in general the power flow equation in the Newton-Raphson method can be write with the help of this equation, where delta pi and delta qi is the change in the active power and the reactive power of the system for the ith bus, or we can say PQ bus, and this is the data that we derived from the Jacobian matrix. So that is hik, nik and jik and lik. This is for the kth bus, and kth PQ bus, the value of this say power angle and voltage magnitude is the delta theta k to change in the vk for the consequent buses of the interconnected power system. Now this is the solution for the load flow studies using NR method. Now the advantages of NR method: the NR method is say faster, more reliable, and it results are more accurate, and it requires a smaller number of iteration for the convergence, and the number of iteration are the independent of the size of the system. Means if we use large number of bus system, then the iteration will be more, and the buses are less in the system for which we are solving the we are giving the solution using NR. If it is having the less number of buses, then it performs the less number of iteration. It is suitable for the large size system. And the disadvantage of the system is the programming logic is more complex than the GS method, and the computer memory required is more to store the data related to the iteration, and number of calculation per iteration are the higher than the GS method. So these are the advantages and disadvantages of the NR method. So thank you very much, student. There is no assignment and no worksheet question after this topic. Once we finish the topic NR method, uh, I will provide you the assignment question and the worksheet question related to this. And if you have any query or any doubt after this presentation, you can solve your query and doubts in our doubt solving session. Also feel free to call me. Thank you very much, student. Thank you all. Jai Swaminarayan.